Hi, my name is Sanjay, and in this video I'm going to show you the working of a Python program that I've created to solve the truss analysis using the stiffness method problems. And I will show you that this program works. But yes, I must tell you that I'm not going to show you the whole code of the program. You have to buy the code if you need it. Okay, I'm going to show you that yes, this code works and what results you are going to get after running the program. And most probably I will compile these codes into a ebook, and I will put that book in Kindle platform, and you can buy it from there. Currently, most probably within few days or few weeks I'm going to do that. So you can buy it then, or if you're watching this video later, after 2-3 weeks from today, then most probably you will get the link in the description box. Okay, so first of all, in order to use this program, you must understand the working of the stiffness method. Okay, so if you don't know that yet, you should go and read the book. At least you should understand these numbering of the joints and the members and this flow direction, how it is put in the problem. So this is the most important part of solving any stiffness method problem. Let me brief you about that. So you have to take care that while numbering these degrees of freedoms, you have to number out the unrestrained joints, unrestrained degrees of freedom within. You have to first number these free degrees of freedoms. I mean unrestrained. For example, here I am numbering here degrees of freedom 1, 2, 3, 4, and 5, 6. So you see that 1, 2, 3, 4, these are free joints. I mean they are not having any support. Okay, there is no roller support or pin support here, there is no roller or pin support here. So these lower numbers 1, 2, 3, 4, these are the lower than the 7, 8. 7, 8, these are the restrained degrees of freedom. You can see that this is a pin joint, so 7 and 8 are not free to move. Okay, these degrees of freedom are restrained, and 5 is unrestrained. So I have not taken 5 along this direction because this is the restrained direction. This joint cannot move in x direction, but it can move in the y direction. So 1, 2, 3, 4, 5, these are the lesser values, so they are numbered first. You could have done like this also, 1, 2 here, and 3 and 4 here, and then 5 here. Or you could have numbered it like this: 1 here, then 2 here, 3 here, 4 here, 5 here. So you have the freedom to number the free joints, unrestrained joints within the range available below. What is the range? 1 to 5. And you could have numbered this like 6 here, 7 here, and 8 here, but you could not put here 5 and here 1 or 2. Okay, I hope you get that idea. If you still don't get, please pick up the book. This example I have taken is from the book Structure Analysis by R.C. Hibbeler. Okay, so you have to understand this part first. Okay, so if you understand that part here, then, and you must also know that these are the member numbers. These represents the members. So 1 in this square bracket, it represents member number 1, and this direction, it represents that I have to take this node number as the near node and this as the far node. So 1 is the near node for the member 1, and 2 is its far node. Okay, and similarly for member 6, 2 is the near node and 3 is the far node. For member 4, 4 is the near node and 3 is the far node. So you have to simply take care of these numbers while running this program. When it asks you to put these numbers, you have to put them accordingly, according to this numbering. Okay, so let us go to our program. this is my program, and this is it is created using this NumPy library, Python library, and this is a smaller library that I have created by myself, and it has less use in this program. You could have you can ignore this if you, I mean, this is only for pretty printing. I mean, when I get float values, I can round them using the various other functions in Python, but I have coded it myself also, and it is somewhat different from the those original functions. Okay, so let us not worry about that. So let me run this program. So first input you have to put here is the unit of length. So what is the length unit? Meter. Load unit, that is kilonewton. All these things are given in the problem statement. AE given, so AE is not given. A is the area, E is the value of the elastic modulus. It is not given in the problem statement, so I will say no. The number of members, it is asking. So number of members, see how many number of members we have. So this is the problem. So this is the maximum, so 6 numbers. So there are 6 members. Okay, and how many joints? 1 2 3 and 4 joints and 6 members. Okay, so number of members is 6 and number of nodes is 4. Then for node 1, it is asking you to put the x and y values. Okay, so x and y values, in order to put these x and y value, you have to choose a particular coordinate system. Okay, you have to choose origin. Okay, so and it is advised to choose the origin such that all the nodal values of x and y, they are positive. So if I choose this joint number 1 as the origin, then x value for 2 will be positive. It will be how much? 2 meter. And x and y for joint number 3 will be 2 meter and 2 meter, because this is 2 meter 2 meter. So joint number 3 will have 2 2, and joint number 4 will be x0 and y2. So all these values are positive. So it is it is easy to solve the problem if these are in the positive. Yeah, in computer it doesn't matter, because computer can do all the calculations, but by hand it becomes convenient, so we will go with that only. Okay, so x value for 1 is 0, y value is 0, and name of the degrees of freedom along I. So you have to put the name of the degrees of freedom along x. Here this is 1. Okay, so this is 1, and along y this is 2. So degrees of freedom are these are the directions along which this node can move. So there are 2 directions, x and y. Okay, so I will put here 1, name of the degree freedom along 1, and along y it is 2. Okay, so for node number 2 is, this is the node number 2. Okay, so I will put it here so that it remains here all the time, and I will minimize this one. Okay, so node number 2 is at x is equal to, this is 2, so this is x is equal to 2, and y is 0, because vertically we have not. So node number 2, x is equal to 2, y is equal to 0. Similarly for joint number 3, okay, so for 2 degrees of freedom, so along x it is 6. See, it is 6 along 6 along x-axis, this is x-axis, and 5 along y. So degree of freedom is named 6 along x-axis and 5 along j-axis or y-axis. And for node number 3, x is 2, y is 2, and along x it is 7, and along y it is 8, and along x it is 7. Okay, so along x it is 7, along y is 8. And for node number 4, this is your circled node number 4, and this is x is equal to 0 and y is equal to 2. So y is equal to 2, and along x-axis degree of freedom is 3, and along y-axis it is 4. So now we have put the node values. Now number of known force degrees of freedom. how many numbers of degrees of freedoms are known. I mean, what do you mean by a number of known force degrees of freedom? I mean, how many nodes have forces which are known. Okay, I could name this something less confusing. I think this is a confusing sentence here. So what it is asking is that how many degrees of freedom are there along which the forces are either given or they are zero. Okay, so 1 and 2, here no force is acting, there is no reaction, so number forces are known here. Similarly here forces are known because along axis is 2 kilonewton, along y it is minus 4 kilonewton, so this is known here. Here along 5 this particular direction, number 5 direction, there is no force along y axis because there is no reaction along y axis, so along y axis force is 0. Along this direction, 6 direction, we don't know what reaction because we yet don't know what is the reaction value, so this is not known, this is unknown. Similarly 7 and 8, along these two directions forces are still unknown because there are reaction forces. So I would say there are 5 directions along which forces are known. So the known forces along initial 5 degrees of freedom. So put the value of force along first degree of freedom. What is the first degree of freedom? This is the first degree of freedom. Along this direction there is no force, so I would put here 0. Similarly along direction number 2 there is no force, I would put 0 here too. Then along 3, this is the 3, so along this there is 2 kilonewton force, so I would put 2. Don't put the kilonewton here, only put the float or integer values. And along 4 there is minus 4. Units we have already put in the initial part. Okay, and along 5 direction, this is the 5th direction, and along this direction there is no force है ना, यहाँ पे there is no force here, so I will put 0. Okay, so for now it is asking you the start node and end node. It has recorded these values: node 1, node 2, node 3, node 4, and xy. Okay, and this all this I have written just to create a complete solution, to give you the details of the solution. Okay, I am writing all these values in order to explain that and this is how I got my solution. So you can use this solution also in your assignment problems also. Okay, so this is listing here the value of the known forces. So along direction 1 0 force, direction 2 0, so I have put these values, and it is showing you the results in the listed values and the corresponding unknown deflections. So all these initial five directions, they would have certain deflections also, and let us assume these deflections are d1, d2, d3, d4 and d5, okay, respectively. And nodal degrees of freedom, these are the numbers for the node 1. Node 1 is having 1 and 2, node 2 is having 6 and 5, node 3 is having 7 and 8, and node 4 is having 3 and 4. So these are the listed values of the degrees of freedom. So now it is asking you starting node of member 1. So member 1, this is the member 1, and starting node is 1 and ending node is 2. So starting node is 1, ending node is 2. Okay, so it has created a global stiffness matrix for member 1. This is the global stiffness matrix for member 1, and its nodes are 1 2 6 5. Oh sorry, degrees of freedom are 1 2 and 6 5. So this is 1 2 6 5, 1 2 6 5. I hope you understand this part if you know what is stiffness matrix. And in more global term, you can write this global stiffness matrix like this. Okay, so this is first, second, third, fourth, fifth, sixth, 7, 8. So there are 8 degrees of freedom, and this matrix in global term it will be 8 by 8 matrix. Okay, and okay, so this I have all programmed this to make it appear like this. Similarly for member 2 starts with node number 1 and ends at node number 3. So starting node is 1, ending node is 3. So this is the for the member number 2. For third member, this is starting node is 1 and end node is 4. Okay, this is third member. Then for member fourth, see, this is the member fourth, starting node is 4 and ending node is 3. So I put 4 and 3. This is for the member 4. And then for member 5, this is the member 5, starting node is 4 and ending node is 2. So starting node is 4, ending node is 2. Then for member number 6, starting node is 2 and ending node is 3. 2 3. So yes, the whole of the problem is solved now. So let us check the results. Okay, so now let me put it like this here. So this is our global stiffness matrix. Okay, this part, let us check it with the results given in the book. So this is our results in the book. Okay, so here you can check the first column, this is 0.678, and here you see 0.6768. alright, 0.1768, 0.1768 minus 0.1768, and you can see the same at this point, minus 0.1768. so you can see that you got all the values same as given in the book solution. And you can also check the last column part also, so you can check it here. Okay, so minus 0.1768, okay, all these values are correct. So yes, we have got the correct global stiffness structure stiffness matrix. I mean, this stiffness matrix, it represents the stiffness of the whole of the truss. This represents the stiffness of truss as a whole. This is not for single member, this is the total stiffness matrix. Okay, I think someone is working out there, sorry for the noise. Okay, so let us check the now support reactions. So support reactions, I have, you can see this, all the matrices, all the procedures, all the processes, none is ignored here. You can see this solution almost as it is given in the book. Okay, so it will show you the whole steps also. Okay, so these are the calculations of the deflections. Okay, and I think these same deflections, they are given in the book. So but we were asked with the support reaction. So support reaction is minus 4.0 kilonewton along 6. So along this direction, support reaction is minus 4 kilonewton. So let us check the value as given in the solution here. So this is Q6, you can see here Q6 is minus 4, Q7 is 2, Q8 is 4 kilonewtons. Okay, same values here we got. And member, for member 2, it has asked us the member in the force in the member number 2. So force in the member number 2, that is Q2, is 2.536 kilonewton, and you can see here 2.54 kilonewton. So it has rounded this 3 to 4, and it has calculated only for the member 2, but this solution, it gives you the member forces for each member, for member 3, member 4. So I have programmed it in such a way that it gives you the member forces for each member. Okay, so up to member number 6 you can get the forces here. Okay, so this is the complete solution. I mean, you will get all the deflections, all the member forces, all the support reactions for the truss. Okay, so I hope this is quite a good program, and you can get it from me if you need it, but only with money. Okay, so that's all for now, and if you need to ask anything related to whatever I have told you in this video, please ask me in the comment box. Most probably I will reply. Okay, and you can write to me at my Gmail ID, that is Sanjay. I will write it here. Okay, I will write it. I cannot write it here, I can write it here. Okay, so my ID is Sanjay 914222 2@gmail.com. okay, so you can write into me at this ID. I hope you have noted it. Alright, so that's all for now. Please stay in touch for more such videos, and